My name is Fergerson, and before I get started, I'd just like to thank the Grakn team for putting this conference together and for inviting me to talk. So thank you guys, it means a lot. My talk is called The Grakn Warrior's Guide to Augmented Software Development. I hope that by the end of this talk you understand what augmented software development is and how you can use Grakn to build such tools. So like I said, my name is Fergerson. I'm the founder of Source++. It's an early stage, unfunded, open source programming assistant. I've been programming since I was 14 years old. I landed my first programming job straight out of high school, and I've been programming professionally ever since, so for about 7 years now. I'm a big advocate in open source software, so basically everything I do these days is open source, but what I find myself most interested in is tools for software analysis, which this talk will cover. So before I get into what augmented software development is and how we can use Grakn to build it, I just want to quickly review how the field of software development evolves, because I think it's important to see the trajectory that software development is on and therefore could likely be headed towards. Software development belongs to the field of computer science, which in a chapter called Computer Science, the Mechanization of Abstraction, Alfred Aho and Jeffrey Ullman described computer science as literally a science of abstraction. They say that the purpose is creating the right model of a problem and devising the appropriate mechanizable techniques to solve it. They go on to say that every other science deals with the universe as it is. The physicist's job, for example, is to understand how the world works, not to invent a world which the physical laws would be simpler and more pleasant to follow. But that computer scientist, on the other hand, must create abstractions of real-world problems that can be understood by computer users and at the same time that can be represented and manipulated inside a computer. Software development is no different, and it utilizes the same process of abstraction to solve increasingly complex problems. So what exactly is abstraction? Well, we could simply say that abstraction is the elimination of the irrelevant and the amplification of the essential. We find that abstraction is crucial in software development because of the amount of complexity present in modern problems. If we were to erase those many layers of abstraction currently present in developing software, we would see something like this. We would get machine code. Machine code represents the first layer of abstraction used to create software. Machine codes are essentially numbers that correspond to specific atomic actions that a computer is able to take. Machine code, being at such a low level abstraction, presents such a huge amount of detail that it's difficult for humans to reason with, even though this is the level of detail that computers require to operate. So to make things easier for humans, for us, we added another layer of abstraction. And we created the second generation of programming languages, which we called assembly languages. These languages allow us to perform low-level actions such as storing and retrieving data, modifying and comparing data with keywords instead of numbers. This simplified instructing computers, but it still required several commands just to do something as simple as adding two numbers. So to make things easier for us, we added another layer of abstraction, which brings us to the third generation, also known as the imperative programming languages. So this is a generation for the majority of the currently popular languages like C, C++, C#, Java, Python, Go, and basically most of them. Most of the popular languages. And the reason being how general purpose these languages are. If a machine can solve a problem, then you can solve that problem using an imperative programming language, given that computers are naturally imperative machines. So imperative programming languages made it much easier for humans to read and write than binary code, but just because we can solve any problem we want using an imperative programming language doesn't necessarily mean we should. And this is because most of the common problems that we encounter when creating software have already been solved. And if we were to write those programs from scratch, we would stop the progress of software development. So to avoid constantly reinventing the wheel, we added another layer of abstraction, bringing us to the fourth generation of programming languages, which are called the domain-specific languages. These languages are primarily APIs written in imperative programming languages, but due to the way they're used and distributed, they essentially function as separate and distinct languages in and of themselves. The only exception being they're not as general purpose as imperative languages, but rather used for a specific task. So each of the fields presented here have libraries that you can use to create and achieve a large amount of functionality in your own applications, which you wouldn't have to implement yourself. So for example, there is the Stripe API in the payment and billing category that would allow you to create entire payment systems using just 10s to 20s lines of code, compared to the tens to hundreds of thousands of lines of code that they would use internally to allow you to do this so easily. But as always, software development is about abstraction. And as we fill in this landscape of things we want to compute, we inch ourselves closer towards generalizing the next layer of abstraction, which are the fifth generation languages, which are the languages that are declarative, constraint, and logic-based. These languages are unique in that you don't tell them what you want to do for each step, but rather what the end goals are, and then leave it to the computer itself to figure out how to get there within the bounds you've set. So these are the languages like Mercury, Grakn, and Prolog. These languages force us to focus on the problems we're trying to solve and articulating what a correct solution to those problems would be. Um, it is then up to the computer to figure out the most optimal way of achieving that. So instead of giving computers imperative recipes for solving problems, we instead give them declarative specifications and have them figure it out themselves. This sometimes feels like an exotic and strange way of talking to computers, but a character from one of my favorite TV shows sums this way of thinking up most eloquently when he says, "Hey, I don't tell you how to tell me what to do, so don't tell me how to do what you tell me to do." And while Bender says it in a very funny way, he makes perfect sense in that he considers it his job to figure out how to do what you tell him to do. This is precisely the way the declarative programming languages work. They consider figuring out the specifics of an implementation their job. As humans, our skill is in understanding what needs to be done. The computer skill is in working out the best way to do it. So this allows us to eliminate the irrelevant and focus on the essential. So that's generally how software development evolves. Now, granted, things get a bit fuzzy after the third generation because of the amount of programming paradigms which are conceptually equivalent. But basically, programming language generation correlates to what type of code you primarily find yourself working with. The first generation you work with memory representation and machine instructions. Second generation you work with machine instructions and algorithms. Third generation you work with algorithms concepts specific to your Third generation you work with algorithms, formal models, and concepts specific to your problem domain. And finally, in the fourth and fifth generations, you'll find and work almost entirely with concepts specific to your problem domain, creating a formal model and working with concepts specific to your problem domain. And a side effect of these layers of abstraction is that each layer reduces the logical complexity necessary for solving a problem. So for example, something that might take 2 million logic gates to compute may take only 250 lines of Grakn to compute, whereas something that takes 2 million lines of Grakn to compute would be practically impossible to implement using logic gates alone. And these layers of abstraction don't just reduce complexity, but as we move away from machine code, each layer of abstraction actually gets us closer to a language that comes more naturally to the way humans represent and solve problems. Machines prefer a language which is exact, like binary. Everything is either 0 or 1. There's no possibility of ambiguity. Humans, on the other hand, enjoy abstract concepts and constantly think about imagined or hypothetical events and think about things in terms of probability. So to communicate more efficiently with machines, we are constantly adding layers of abstraction. These layers of abstraction do have other side effects though. As we get rid of the irrelevant and focus on the essential, a lot of the underlying details become out of focus and a bit vague. For example, I could say the red apple I had for breakfast to represent a very low level of abstraction. If we move up a layer of abstraction, we're now just saying red apple, up another layer apple, up another layer fruit, and then simply produce. Now, if I asked you what I ate and when I ate it, and I only told you produce, you're gonna have a very difficult time figuring out it was a red apple and it was for breakfast. But this is the level of detail that computers require to operate. If something is vague for a computer, we can expect it to magically figure it out for itself. Thankfully, being abstract is something that's profoundly different from being vague. The purpose of abstraction is not to be vague, but to create a new semantic level in which one can be absolutely precise. For example, if instead I told you I ate produce in the context of fruit, fruit in the context of apple, apple in the context of a red apple, and a red apple in the context of the one I had for breakfast, then there's a chain of reasoning in which you can follow and understand that when I say produce, I mean the red apple I had for breakfast. So this is the basic idea behind each generation of our programming languages. When we look at a few implementations of the Fibonacci sequence, we can see that the higher the generation, the more abstraction we get. In the machine code, we solve the problem using memory representation. In the imperative code, we solve the problem using algorithms. And in the declarative code, we solve the problem while using a formal model. Each implementation is more abstract than the previous, but definitely not more vague. Each implementation is actually more semantically precise. Now, if we compare the actual formula for the Fibonacci sequence, it's pretty obvious that the declarative language resembles the formula much closer than the imperative language does, than the machine code language does. And this is not a fluke either. The formula is the most concise way we have of describing the Fibonacci sequence. So if we want to mechanize that process in the most unambiguous way, then ideally it should look as close to the formula as possible. This becomes even more evident when you understand that the act of describing a program in unambiguous detail and the act of programming are one and the same. If there's one thing you remember from this presentation, I hope it's this. As time goes by, programming languages become more abstract and as a consequence, much closer to the languages we naturally use in much closer to the requirements and formulas we naturally use in human language. But ultimately, the act of programming has always been and will always be about describing requirements clearly enough for machines to execute. How we express those requirements is the only thing that's changing. And a side effect of us moving towards programming languages which more closely resemble requirements is that we are starting to instruct computers less on how to perform and more on what to perform. This is because requirements most naturally describe what needs to be done. For example, if the requirement is to get to A to B, then there can be several ways of actually achieving that, but ultimately the requirement is to get from A to B. But before the common way of instructing computers goes from telling them how to perform, we we first need to teach them how to create these imperative instructions for themselves, which essentially means teaching computers how to program. And this is possible, but it's going to require that computers understand and maintain the context of the requirements we give them so they can produce the correct translations. Context was much easier to hold in the first few generations because these essentially boiled down to keyword replacements. Instead of numbers, we use keywords, and then instead of keywords, we use keyword combinations, which we called instructions. But now we're trying to move from instructions to requirements, and this gap is much larger to cross than the previous ones. So this is where I see augmented software development coming in. So what exactly is augmented software development? Really, the idea of augmented software development is to use artificial intelligence and machine learning to automate code preparation, validation, and generation. Basically everything your standard software developer does. Being such, augmented software development also goes by other names such as knowledge-based programming assistant, automated programming assistant, automated software engineering, AI-based pair programming, and virtual software developer. So the first question I'm often asked whenever I mention the possibility of a virtual developer being a thing is, so is it like Clippy? And the answer to the question is kind of, but not really. Clippy was fairly ambitious, but it mainly served scripted responses based on Bayesian algorithms. If you typed Dear Bob, it would guess that meant you were writing a letter and offer help about letter writing, but that often seemed to be more annoying than helpful. Beyond that, Clippy only helped with ideation. It watched what you typed to try to guess what you're doing and assist, but it did that based, again, on probability rather than comprehension. So in order for it to be helpful, it needed you to be as predictable as possible. And if you weren't, any advice it would offer would seem irrelevant. On the other hand, augmented software development is about enhancing and automating the entire process of software development. From coming up with the ideas, validating them, building them, testing them, deploying them, and maintaining them. The first of these phases of software development obviously being deciding what ideas to implement, which is the ideate phase. Now, if we break down the ideate phase, we can see it consists of 3 stages: ideation, prototyping, and validation. Augmenting this phase of software development, we could imagine tools which, if you ran an e-commerce website, were able to notice that when the system performs slower, there are significantly more users dropping off during your order funnel, and it would use that information to search for, test, suggest, or possibly automatically implement changes which would specific performance enhancements that would actually ultimately increase your sales. Now we have the build phase, which makes up the requirements development and testing stages of software development. Augmenting the build phase, we can imagine a situation where a software company inherits legacy software with little or no documentation, and instead of dedicating countless man hours towards it, they could instead give it to a virtual developer who analyzes the total usage and function of the system, and is able to automatically generate documentation and test based on how it currently functions. This would make it much safer and easier for humans or additional virtual developers to come in and change, knowing that there exists this safety net which will ensure they don't break something. And then finally, we have the run phase. This phase consists of the deploy, monitoring, and maintenance stages of software development. So there's a lot of ways to augment this phase of software development, and there's already a lot of work going on here, which you probably might be already using. But for this phase, we can imagine self-healing software systems which can intelligently roll out updates or scale up and down based on user loads, and software systems which can identify which areas of your application are not being used and can likely be removed or deprecated. That doesn't sound as exciting, considering there are companies that already do this, but what I want to emphasize is that augmented software development is about the whole process of software development. What we have now are mainly localized augmentations. The idea of augmented software development is to essentially create virtual developers which are able to simultaneously handle all the stages of software development. Something that uses what it learns in one stage to make better decisions in other stages in the way that an actual software developer might. We would simply give these virtual developers the requirements via declarative specifications or higher abstractions, and they would handle actually going through the process of software development. And that all sounds great, so then the question becomes, how can we build augmented software development tools? Well, I think there are essentially 4 areas of automation that these tools will need to be able to perform. 2 of them are necessary for the ideate and build phase, those being source code generation and verification, and 2 which are necessary for the run phase, those being source code comprehension and dissemination. So now I lack a formal degree in computer science, so you should probably take everything I say with a grain of salt, but I do have a vested interest in source code analysis technology, and there are some features that I think will be most useful for realizing useful augmented software development tools. For starters, I think they'll be language agnostic. As long as we have tools which only work for specific languages, we've basically proven that they don't understand the underlying concepts. So these tools should have an understanding of the core concepts so they can easily adapt to languages that they've never seen before, as long as those languages share concepts that they've seen before. I also think these tools should have a unified knowledge representation and combine knowledge from many different sources to not only understand how code works, what code does, but also how code behaves in its operating environment. I think they'll be fully integratable with existing static and dynamic analysis tools so that they can utilize tools that already work and extend them, and rather than rewrite them from scratch, allowing them to not reinvent the wheel. And I believe they'll use guided models that can change and build over time, models that can be personalized per project and domain. So for example, you could say that these type of variables are used as account passwords, and then enforce rules about what those type of passwords can and can't do. And finally, I think they won't just scan and analyze code during or after compilation, but rather during the process of software development. They'll work alongside developers and offer assistance as code is being written, consider while code is being written is the most optimal time to actually change and improve it. So essentially what I'm talking about is building a fairly intelligent system. And if working with Grakn has taught me anything, it's that building intelligent systems starts at the database. Source code is a very complex medium, and it's more difficult to efficiently store than simple tables or key-value relationships. Source code has encapsulation, hierarchies, types, modules, packages, and a bunch of other explicit and implicit relationships, which would need to be modeled. Trying to store these relationships in SQL or NoSQL databases quickly becomes messy. Grakn, on the other hand, allows us to define these relationships naturally. It internally handles concepts like hierarchies, types, attributes, relationships, roles, and inferences, all things that would require more tables to build in a SQL database or a large amount of external logic to build in a NoSQL database. So this makes a knowledge graph the obvious choice of storage for source code for analysis. And as it turns out, source code can actually most naturally be expressed as a graph which is commonly begun by using an abstract syntax tree. We normally then enhance this structure with additional control and data flow graphs and other types of graphs, but for this presentation I've kept it very simple and I'm only using the abstract syntax tree. Normally these graphs would be a lot more connected though. So here we have some simple Python code which computes the Fibonacci sequence and the abstract syntax tree it produces. There is a problem though, and that's that storing source code based on the abstract syntax tree presents a problem basically. And it's given that each programming language has its own syntax, the graphs they produce look similar, but they aren't isomorphic. This means that even though all three of these code snippets do the same exact thing, the graphs they produce aren't the same. So any queries that we execute against one language won't be fully compatible with other languages, meaning that we won't be able to perform actual language agnostic queries. And it creates the need for transforming these tools or transforming these code snippets to a universal format. However, our hope is not lost, given that each of these code snippets does the same exact thing. There is an underlying structure which they all follow, and we can see that structure a lot easier if we color the nodes which are semantically equivalent. So here I've colored all the method declarations as salmon, and all the function argument references as yellow, and all the biconditional statements as white, all the return statements as black, all the recursive method calls as pink, all less than operators as blue, all minus operators as orange, and all plus operators as red. And finally, all numeric literals of 1 as brown and all numeric literals of 2 as green, leaving everything else purple. At this point, we can see that there is a common structure between them, and this is a structure that deals with the semantics of the code, which doesn't change based on the language. A function is a function regardless of the language. A Boolean is a Boolean regardless of the language. One language may use true and false to represent Booleans, another may use 1 and 0, but the underlying concept is the same. And these are the things that we can use and work with in a language agnostic way. So if we then strip away all those purple nodes, which mainly dealt with syntax and program structure, what we're left with is this, something that only deals with the semantics of those languages. And given that each of these languages does the same thing, solves the same problem in the same way, they're semantically equivalent even if they aren't syntactically equivalent. So this is a structure that we would need to save in Grakn and work with, and we can derive this structure if we had something which could create something like a universal abstract syntax tree. And this is precisely the idea behind a project called Babelfish. This is not a project I created, but a project that found me at the most opportune time. Basically, I knew that I needed to save source code in Grakn in a language agnostic way, but I was finding it actually very difficult to achieve. That's when the creators of this project reached out to me and told me they were working on something that might interest me. Babelfish describes itself as a universal code parser. Basically, Babelfish is able to read source code with support for 10 languages, 6 more in development, and create universal abstract syntax trees by extending native abstract syntax trees with semantic roles annotated on each node. This essentially creates a structure that stays the same despite the programming language. Babelfish accomplishes this by reading source code and breaking it down by the following list of roles. As of now, there are 120 of these roles, but they are combined with each other to further signify the meaning of each piece of code. For example, we could have an if statement, which may only have the if role, but inside that if statement, we could have a body of code that has the roles if and body, meaning that this body of code is not just a body of code, but it's a body of code that belongs to the parent if statement. Using Babelfish, we can effectively remove syntax from the equation, and as a plus, any tools that we create using Babelfish can work on new languages that we've never had them work on before without us making any modifications. All that's necessary is for Babelfish to add support for that language, and once that's done, we essentially get support for that language for free. We can see Babelfish in action if we parse some source code. So these 5 lines of Python code produce 31 unique roles, which are used a total of 117 times. This is because, again, the combination of roles is what ultimately describes or determines the full meaning of a piece of code. So they're very likely to be roles that are used a lot more than once. These semantic roles are annotated on each node of the native abstract syntax tree. This allows us to ignore the syntax of the code and creates a structure that we can be interrogated in a language agnostic manner. So Babelfish creates this language agnostic structure, which is then stored in Grakn. Grakn is then used as a knowledge base and allows us to perform deductive reasoning over the source code stored inside of it. So using only Babelfish and Grakn, we could write this very simple query, which when executed will give us all the function arguments for any function stored in Grakn, regardless of what language it's written in. What we'd be looking for are any function or any nodes which have the function, argument, and name roles simultaneously, which would only be true for actual function arguments. But let's say we wanted to write something which would find and verify a function that correctly implements all the logic necessary to produce the Fibonacci sequence. Doing so would mean finding the rather complex semantic graph we saw from the previous slides. We could write a query which would find this graph using pure Grakn, but we would end up with something like this. As you can see, the logic necessary to verify the correct implementation of the Fibonacci sequence is rather verbose. It takes about 15 lines of Grakn just to grab the nodes which are only function declarations. This query is, of course, language agnostic, which is the reason it takes so much logic, but this is still way too much to be efficient for verifying a much larger amount of functionality. So to alleviate this complexity, I created a tool for further translation called Arthur. Arthur takes the verbose form from Babelfish and it identifies and labels structures it's aware of. So using Arthur, we can take this long query down to this. This is much simpler to write and reason with because it takes the structures which take several lines of logic to reason with using semantic roles and gives them a formal structure. So now we can query for functions using a single line of code because Arthur has already performed the logic necessary to identify and label the nodes that meet the semantic roles requirement to be a function. So Arthur does the same thing for much other concepts like recursive function calls. So instead of all the logic necessary to identify a recursive function call, you would simply refer to it as a recursive function call in a single statement. And so eventually the goal of Arthur would be to identify and label even higher level concepts so that we could find functions that implement specific functionality like the Fibonacci sequence using only a few lines of code. Arthur plans to achieve this goal by becoming an ontology and repository of common programming concepts and algorithms, starting with small patterns found in code and using composition to identify larger concepts. So there's still a lot of research on the most optimal way of recognizing algorithms and program comprehension, but the majority of approaches that I've seen that have success involve using pre-existing knowledge bases of programming concepts and algorithms that are used to identify structures using bottom-up and top-down approaches. So these are the type of techniques that Arthur will eventually be using to identify higher-level concepts by itself. For now, though, it's just focused on providing a formal model for the most basic structures of code, but the goal is to eventually include common design patterns in Arthur 2.0 and common algorithms in Arthur 3.0 in later versions. This would then bring us to a point where we can do higher-level concept queries. Babelfish breaks down the source code into language-agnostic structures. These structures are stored in the Grakn knowledge graph, and Arthur searches for and annotates higher-level concepts that can be statically determined. Of course, not all properties of source code can be statically determined. Something like runtime information would involve actually running the code to collect, and thankfully there are already many tools that can do this. And this is where another tool I created called Phenomena comes in. Phenomena integrates with existing tools by either executing them itself or pulling data via their APIs. It then takes this data and extends the existing structures already in Grakn with the information it receives. In this example, we can see the Fibonacci sequence function from before, but with an additional node of method runtime summary. So this node was derived from a project called Apache Skywalking, which is an application performance management tool that monitors and traces code during execution. So this information is then summarized and correlated with the source code that it pertains to, allowing for an extra dimension of data to be queried along with the source code structure. Phenomena also integrates with existing static analysis tools as well, like Kite. Here, Phenomena use Kite to correlate two functions from different programming languages. The Go code in the right calls the Java code in the left via RPC, and Kite is able to detect this execution and outputs its finding via a number of different formats. Phenomena then takes this data from Kite and integrates it into the structure stored in Grakn. So this allows even further analysis to be performed because of the existence of these cross-language references. So now we not only can query source code based on its structure and its runtime properties, but also based on its usage, even if that's across multiple languages. So this is the basic idea behind phenomena. Phenomena integrates with existing tools and takes their findings and correlates them to the language-agnostic structure stored in Grakn. This creates additional dimensions to explore and ultimately allows for more complex queries to be performed, thus creating a place where there's a large amount of context which cannot be extracted from any one tool alone. We can then explore source code based on several different axes of knowledge. With this technology, we can not only know that something is a function, but we can know that it's a function that implements the Fibonacci sequence, and we can know that that maybe it takes 20 seconds to run if you give it an input value of 1,000, and we could know that the location of the source code calling with input value of 1,000, even if it's from a different programming language. So that's a lot of context we can use the query against. So this is my vision for the inner workings of an augmented software development system. Babelfish breaks down the source code into language-agnostic axioms. Grakn is used as a knowledge base for these axioms. Arthur combines these axioms to create high-level concepts, which it annotates and saves inside Grakn. And then Phenomena uses existing source code analysis tools to extend those high-level concepts with additional information. Babelfish, Arthur, and Phenomena all use Grakn to create a knowledge graph of information about source code, which has gone through several layers of enhancements and extensions to give as much context to source code as possible. This highly contextual knowledge base is then used for a single purpose, and that's to provide real-time assistance to software developers. And that's currently accomplished with the project I've been working on called Source++. So Source++ is an open source programming assistant with aspirations to one day become a full-fledged virtual developer. Currently, Source++ works something like this. We start with a software developer's IDE. As a developer creates new source code, this source code is read by Babelfish, stored in Grakn, and labeled by Arthur. Phenomena is then used to integrate any additional information which can be correlated with that source code. And this all happens on a server outside the developer's IDE, so at this point, everything seems pretty much normal to the developer writing code. Finally, when there is some information that could provide value to the developer, this is sent to the developer's IDE as they're working on that source code, which the information pertains to. This is done by creating a little icon in the gutter of the IDE near the source code the information is about. The developer can then choose to see this information via a keyboard shortcut or by clicking on the icon that appeared. So this would bring up a pop-up above the code which the information is about and gives the developer deeper insights into the code which they could not get by reading the source code alone. Normally, a developer would need to download logs or view monitoring dashboards and various other sources of information and various other sources to get this information. Instead, with Source++, they get this information handed to them precisely where and when they might need it. So for an example of how this might work, let's say we've deployed some code that contained a bug. Presented here are two methods, one which contains a bug and another which doesn't. It's a fairly obvious bug, but I would argue that this bug becomes even more obvious with a tool like Source++, which, when this bug occurs, would add something like this to the IDE. So this essentially singles out the method with the bug, so now it's even easier to see where this bug is, but we can get even more information about this particular bug by clicking the icon that just appeared above the method. And we can see that the last several calls to this method failed. We can click on one of these failed calls, and we can see that it's failing because of a SQL select call. We can select that call and see that the reason it's failing is because of a PSQL exception. So at this point, it's fairly obvious what the issue is. Looking right above the error, we can see that the select statement we're executing is missing a space between from and account. If we still weren't able to figure it out, though, we could get the classic exception stack trace by clicking the error, and we get a more detailed explanation about the issue that's occurring. Again, this is information that would typically require you to go to monitoring dashboards or search logs. Instead, this information is placed right next to the problem code, so the developer never needs to leave their IDE. And while that can be useful, that's not exactly real-time assistance. So this isn't something that Source+ can currently do, but this is something that I'm hoping to do soon. And we can see an example of some real-time assistance with the following scenario. So the bottom method of this code is called update account information, and it's used to save updated account information. Sorry, the quality is so bad up there. We can imagine a scenario where a developer wants to update this method to not only save updated account information, but to email the account that's being updated to let them know about the change. So let's watch as a developer adds one line of code, which will send a notification email whenever someone updates their account information. So the developer adds a call to notify account updated. And notice that the moment the developer finishes writing this code, Source++ adds a little turtle icon above the code. The developer hasn't deployed, committed, or even saved this code change, and yet they're already being told that this change will result in a significant performance decrease. So this seems a bit odd, so the developer decides to take a look at what kind of performance decrease we're talking about. So they click the turtle icon, and up pops a performance chart, which shows the average response time of the method in question. They can then hover their mouse over this chart and see that the two distinct runtimes are being displayed. One for the actual response times, which are shown to average out at 310 milliseconds, and another for the expected response times, which are expected to average out at 30 seconds. So this means that if we were to deploy this code change, we could essentially expect all calls to update account information to slow down by over 9,000%, which is fairly significant. The developer can then get a more detailed explanation about what's causing this problem by clicking the expected average response time. And here they would be able to see that the call which is causing the performance decrease is obviously the new method they just added, the notify account updated. They can click that method and they could see what the performance issues, they can look into the performance issue further. And they can see that the performance issue is coming from a method called getMailSender. So in this instance, it turned out that the getMailSender method was actually creating a new connection, connecting to the mail server, and performing tests each time it was called, something it was only supposed to do the first time it was called. So the developer could see this is obviously a mistake, and they update the getMailSender method to perform correctly. After fixing the issue, the developer then would go back to the code that they originally changed and notice that the turtle icon has disappeared. Instead, they would now find a new rabbit icon above all the methods that they've significantly improved, which I think would be pretty cool to see. Once they've committed their changes, all these icons would disappear, and to see them again, they would need to significantly hinder or improve further functionality. So there are a few other features I could show, but I think it's pretty obvious that this technology is still in a very early stage. What I've demonstrated in this presentation primarily shows how source code can be comprehended and disseminated, but the goal of augmented software development is to create virtual software developers that can actually handle the entire software development lifecycle. The tools I've created so far don't generate or verify source code, so there's still a lot of work that needs to be done, but this is the direction that I believe we're headed towards in software, and I don't think it'll be very long before we have actual virtual software developers becoming commonplace. I certainly hope that virtual developers will become a staple of the software development community, but I've talked to software developers who have a similar disposition to those from this quote. They think that augmented software development tools mean that we're close to the end of code, that soon all code will be generated instead of written, that programmers simply won't be needed because business people will generate programs from specifications. And this leads them to question, when will human programmers become obsolete? And for anyone wondering when that will happen, I have one more quote from Uncle Bob, and that's to remember that code is really the language in which we ultimately express the requirements. We may create languages that are closer to the requirements. We may create tools that help us parse and assemble those requirements into formal structures, but we'll never eliminate necessary precision. At some level, those details cannot be ignored or abstracted. They have to be specified. And specifying requirements in such detail that a machine can execute them is programming. So programmers should know they have very little to actually fear. As long as there are machines to program, we will be there to program them. We will simply focus less on the irrelevant and more on the essential, just as the process of abstraction has taught us since the very beginning of software development. That's my talk on augmented software development. Thanks for listening. Thanks for coming.